Sign language is the main communication from among deaf and the hearing impaired people. The sign gesture is mainly composed of 3 components: hand shape, movement, palm orientation, and location. Unfortunately, very few people with normal hearing understand sign languages. And existing communication approaches like sign language interpreter writing on paper, they have key limitations in cost, availability, and convenience. Therefore, an automatic sign language recognition system is highly desirable. The system usually captures the sign gestures by sensor like cameras or wearable sensors, and then translate the gestures into text or speech using some models. Many efforts have been done during the past decades. Vision-based methods also get high accuracy, but they may not work in dark and may not work in anywhere or at any time. The methods using data growth, maybe they are intrusive and inconvenient. Methods based on very ambient provide a more natural and convenient manner. However, most of them focus on user-dependent scenarios, and the performance will degrade generally when the user is new to the system. Moreover, these methods perform only single word recognition rather than for sentence sequence translation. In this paper, we present MyoSign, a deep learning-based system that enables user-independent end-to-end American Sign Language recognition at both word and sentence levels. We leverage a lightweight off-the-shelf wearable device, MyoArmband. This figure shows a typical application of our system. When a deaf person wearing the MyoBand communicates with a hearing people, our system translates the performing gestures to spoken English via a smartwatch, and meanwhile, the speech recognition system translates the spoken English into text in the smartwatch. The MyoArmband contains 3 inertial sensors and 8 EMG sensors. The inertial sensors is good at capturing movement information, and the EMG sensors does well in capturing muscle activity patterns, which can be used to distinguish like figure movement. There are some challenges we need to solve. First is user diversity. Different people have different gesture performing habits, and their muscle tissues is also different. The second is sensory data fusion, as our system collects sensory data from 4 modalities, 3 inertial data, and EMG. Different modality perceive sign language from different perspectives and own distinctive signal and noise models. The third is how to recognize sign language in an end-to-end recognition. In other words, do not need to pre-segment these gestures, because The pre-segmentation is very inconvenient for users because users will not pause between the two words. To deal with the above challenges, we developed a unified deep learning network, which is comprised of 3 models: multimodal CNN, convolutional neural network, and bidirectional LSTM and CTC. Then I introduce these models. First, we split the continuous data into data clips. For each clip, we design a multimodal CNN to learn intramodality and cross-modality. We first apply a 3-layer CNN on each individual sensor data, and then use a 3-dimension CNN, learn their cross-modality relations. We model the temporal dependencies of the input sign language sequences using RNN. Many ASL signs share very similar characteristics at the beginning. For example, want and what in this figure. The similarity is inclined to confuse traditional RNN. So we implied a bidirectional RNN model which performs inference at each point of the trajectory based on both past and future trajectory information. A word sign gesture generally contains 3 temporal overlapping phases: preparation, nucleus, and retraction, of which the nucleus is most discriminative. We should design methods which can automatically rely on the nucleus for classification. As for sentences, it is hard to per-segment the whole sentences into individual words, as the user will not pause between adjacent words. MyoSign adopts a probabilistic framework based on Connectionist Temporal Classification for end-to-end translation. The CTC-based framework makes MyoSign to get round temporary alignment between the input and the output for both word level and sentence level. We collect the word dataset from 15 volunteers and get about 10,000 samples. We perform user-independent tests. There exist great challenges when it comes to user independence due to the individual differences, but MyoSign can still get an outstanding result. Then we compare MyoSign with other algorithms. Among them, 2 are traditional algorithms, random forest and SVM. We also design 5 other deep learning models, which are the variants of MyoSign model. By changing 1 or 2 design components in this architecture, these comparative results reinforce the necessity of our design components of MyoSign. We also construct the sentence dataset and perform user-independent and ANSI sentences test. The average accuracy is 93.1% for 15 volunteers. We also evaluate the recognition performance of MyoSign for ANSI sentences and compare it with other methods. The average accuracy is 92.4%. The impressive results further confirm the effectiveness of MyoSign in end-to-end sign language recognition and eliminate the burden of collecting all American Sign Language sentences. As a conclusion, we propose a non-intrusive variable system that enables end-to-end American Sign Language recognition at both word and sentence levels, and design a deep learning network supporting sign language recognition with robust, user-independent features extraction, effective modality fusion, and no requirements for temporal segmentation. MyoSign achieves an average accuracy of 93.7% at word level and 93.1% at sentence level in user-independent settings. Oh, that's all of my talk. Thanks for listening. I'm glad to take some questions.
I have a lot of questions, but let me start with a very basic one, which is in your transcription here on the slides, you always showed the output as English words, but are you transcribing English words or transcribing ASL words?
No, we haven't done this part job. We just translate sign language to English text.
So the output of the network is actually English, not ASL. Is that what you're saying?
Pardon?
What I'm trying to say, okay, let's, if I have an analogy, that would be speech recognition, right?
Yeah.
Suppose I wanted to speak English and translate and get an output in German text. I could have an end-to-end system end-to-end system that's trained on English speech and produces German text, and it'll be kind of speech recognition and machine translation together. But practically, people find it very useful to have one system which transcribes the English into English word text, and then have machine translation that translates the English to German. So my question is here, if you take this analogy, is your system transcribing ASL signs into ASL words written, or is it doing the transcription and translation to English in one step?
In one step.
One step, okay. So my next question is why?
Because if we translate it into words firstly, and then combine these words into sentences, it should do some pre-segmentation. The segment the words, and then combine it to a sentence.
Okay. I'm not sure I fully understand, but is there a...
Yeah,
maybe we'll move to somebody else.
Another question, we can circle back and maybe after the session. Yeah. Are there any questions before we have a couple of minutes still? Yeah. Okay.
Yeah, thank you for the talk. In your slides, you said that you had 70 different words that you were recognizing. So is this correct that the vocabulary was only 70 words?
70.
So I think I saw somewhere that you had like 70 words that you were recognizing. Still back.
So could it be louder?
So, could you answer that? What kind of vocabulary were you using? How big it was?
How big? Because?
So how?
Previous slide, is that what you're trying to get to?
Yeah, if you go previous.
Go
Back.
Back.
So here.
Okay.
Yeah. So 70 words. So. So I was just asking that why were you using this kind of small set of words?
Yeah, because we choose the most frequency were 70 words, and we think this can be extended later to more words. And then, so are you asking me why why we choose that these 70 words?
Yes.
Because we choose the most frequency 70 words.
Were the sentences also using those 70 words?
Yes. It's
Okay.
also using these 70 words, and some sentences is not included in the training set, so we introduce it as on-C sentences.
Are these 70 English words or 70 ASL words?
70 is equal. A sign language words is equal to English words. Like what sign language, and the English is want to.
Yeah, so I think we'll end about now, so we can move on to